Hello, this is a video walkthrough of Chapter 2 of the book Applied Statistical Analysis for Psychology and Human Factors in R, a graduate course. If you want a copy of the book, you can go to this web page. It's downloadable here under this link. Here's what it looks like, and you can follow along. Also, you can go to this web page, and there's going to be a link in the notes to download the specific code. It'll be under Chapter 2, Handling Data, Sorting, and Aggregation, underneath the link to the video, which will be the one I'm making right now. So if you click here, it'll send you to a page with the materials for Chapter 2. Download these into somewhere convenient. This is something that's generated, and Chapter 2 walkthrough will be a file that contains most of the R code that we're going to be using in this chapter. I've loaded it into RStudio here, and so we can get started. So this chapter is about loading data, handling data, managing data, and this is one of the really useful things to learn in R, because it can take a job that may have taken you days or weeks of manual labor, and sometimes in 1 or 2 minutes you can do the same thing. I've literally seen researchers hire undergrads to sit copying Excel columns around tediously by hand in order to do the same thing that we'll learn how to do really easily today. And so what we're learning today is not going to be any inferential statistical analysis, but it's something that these are things that I do every time I do a data analysis. And so it's very important, and it can be a huge time saver if you know how to do it right. If you don't know how to do it right, it can be a huge annoyance. The other thing is many stats packages don't have capabilities like this at all, and so you may not recognize what's even feasible if you don't learn it in a system like R. So first we want to be able to bring data in. So the previous examples we just made data programmatically or typed it in, but how do you read data in? Now normally you'll have it in a file of some sort. And so I showed a couple files. They were text files. This is one common way to have data stored as a text file. You may pull it off the web, or you may download it from somewhere, or you may create it as a text file. These text files, let's see if we'll look at one of these. It's organized so that a space is the delimiter. There's a header row, and these are not fixed width columns, but Excel could read this in if you tell it to use a space as a separator, and it's not too uncommon to have data like this. So it's a few hundred rows. Each of these columns represent a different data. We'd like to bring this in to R and do it in a way that creates a data frame. So now one way you can do that is actually through RStudio. If you're a little fuzzy about what the commands are, you can always go to RStudio and have it read things in. And so all right, I had a little trouble finding it because I think they've moved this around occasionally, but at least in this version, under File, Import Dataset, there are some menu options to import data. And there's a couple that you can go from text, base plus reader, which is a library. We'll just use the base, but you could also pull data in from Excel, SPSS, SAS, or Stata. And if I were doing any of these, I'd probably go to the menu to bring it in, because these can be really fussy to get right. But even after I do that, it will create some syntax that I can then run in the future. So let me go from text. Let's see what happens. It will ask me to specify. So everything I'm working on is in this folder here, and I'm going to just load this. gives me a little view on this, and then can say, oh, encoding automatic heading. There's no heading. It detects that properly. White space separate, decimals, period, quote, double quote, comment, none, NA strings, NA. Strings as factors. Yes, I don't have any strings actually, so this will be really easy. I can say import. All of a sudden this appears here. It's called C5 data, and it appears over here. And here is the command it used to create this. So I might copy this then and paste it into my R file. And in fact, the one I had saved before is almost the same, but now this one has a few other arguments. This, for some reason, it used to put quotes around it. Now it doesn't. But here's a handy way of loading it, and if I want to load it again, I can load again. So if I filter it or something and I want to get back to the original, I can do it again. This is obviously not in the right spot, but because if I want to load it just not using a absolute directory like this, I can specify C5 data and then make sure my working directory is a source file, and because this file is in the same directory here, it should be able to find it directly. So both of those are easy ways to load a data set. This is read in as a data frame. It's a bunch of variables that have the same number, but they're unrelated. They could have different types. And by default, it's going to name my variables v1 through v14, which is reasonable because it had there were no variables there to start with. There are no variable names there. I actually can load it. I can look at this. I mean, I can't edit it. I'm trying to type here and I can't edit this. But if I see an error for some reason, I can, let's see, file, open, and open one of these files. And it'll just open as a text file, and since it's a text file, I could change things and edit it. Maybe for some reason some extra lines got in there or something, and I change this, and then I rerun this, we should be able to see this change over here. I don't even remember what I changed. 7. All right. So that 7 here is what got changed. All right, so that's an easy way to load things in, and it's actually two ways because you can do it from the menu and it'll create the line, and then you can save that line and have it in your file for the future. To look at the data, I would often, you can just type C5 data, but then the whole thing is printed out and it'll truncate after a certain number of lines. But you can say head data and head of C5 data, and it'll print out the first 6 or so rows, so you can see what it really looks like, and you will also see the header row. Okay. Now you don't have to call it C5 data. That's just how this dialog did it. We could have called it data. You could have called it anything you wanted. But this is a handy way to start. Now the problem is we want to put headers on this. We don't want to refer to these things as V1, V3, V6, because that's a really good way to make mistakes. It's a really good way so you want these labeled something meaningful. It turns out that these are the labels for these columns. So I can load this with column headers in a lot of different ways. So I'm just going to create this set of this variable called head. There's nothing special about that, but it's a list of characters, character strings. And then if I give the read.table the call.names argument, and then look at data, it reads it with those values. If I want to, now the one thing, let's see, head of data. If I want to refer to any one of these variables, I could go data dollar step, for example, and this will just print out that one column. Now, I could also assign it afterward. So here's data without adding that. So head data, and you can see it has those v1, v2, v3. But if I do this, and this is kind of a weird syntax, but it works. And I'll show you that in just a second. If I look at head data again, you can see it's named all of those. Now, so what this is doing is it's a function applied to data, and it's accessing the column names, and I'm reassigning them to whatever's in this variable head. So this is how you do it afterward. But you should be careful when you're reading data with and without headers. Here is data. C5 data 2 actually has the headers in it, and that's often the handiest way to do it. But so here's the data with the headers. This is handy, but if you have a bunch of files from a bunch of participants or something, then you might end up getting rid of all those header files, and it can be annoying as well. So, but you have to be careful, because what if I read this and I turned header off? Now it's read it. I said there's no header. The header becomes the first data. The columns are named based on v1, v2, etc. And the columns become these. And furthermore, because there's a character with numbers, these are actually all numbers, or maybe even factors. So if we look at data v1 or v1, it's a factor with 2 levels, 15 in subcode. So that's an easy way to screw up. Here's another problem you might have. Here's the one without the header. And if I load in and I specify that it does have a header, even if it doesn't, that first row automatically becomes the header, but it can't use numbers as headers, so it appends an X in front of it. And obviously we're missing the first row of data, which might not be such a big deal, but you're using data as the header, and the headers are incomprehensible, so you want to try to avoid that. There's other arguments, like if you have, sometimes your data files have instructions or descriptions at the top. You might pull them off the internet or something, and they have that. And so you can skip rows at the top, including if they have really bad column names. So here I'm taking that one with the header, I'm skipping it, and now if we look at data, you can see it reads it in, even though the original data had the header, with these v1, v2, and then I can add the header back in. All right, there's other ways you can read data as well, and actually before we can use this, we need to create a file. So if you have a data set, and I've got 2 of them, C5 data and data, and I want to write it out to a file, there's functions that will do that. There's write.csv and write.table. So I'm going to run both of those, and you can't see what happened until you go look at the folder. So here I just wrote data.csv, and let me try to open that with just a text editor. So here it wrote out a CSV file with the header, with something that wasn't in the original data set, which is sort of row numbers that are as text, and it's not labeled here. and writes it out in a comma separated fashion. I could load this into Excel really easily. But the other one, let me open it through here. So this does a similar thing, but uses space instead of commas to delineate it. So now I have a new data file that I could create, and a CSV file is often handier because it can be less fussy. A CSV file separates cells with commas. So if you have a CSV file, you can use that read.table again and tell it the separator is a comma, or you can just use the read.csv, which is almost the same thing, although it does have some advantages. In this case, I guess we should do C5 data. And I can now read it in with the either the read table or the read CSV. Now if we look at dat2, it looks like all the others with the proper columns, and it has this extra column because I saved it out, and R, when it saves it out, puts that extra column in. Okay, so that's just a basic overview of the different ways of reading in and writing out structured data to files. And so typically at the beginning of any analysis file, I will have a function like that, read CSV, that reads in the data. This way I don't have to use the project. If you use a project, it will save the data automatically, but you still have to get it in somehow. All right, so the next thing we want to do is look at different data structures, more complex data structures, and how to understand basically what's going on with them. So to do this, we're going to look at a data set that's automatically built into R, as long as we can call it. So it's sort of embedded within the R system. It's called trees. So if I do data trees, that trees will be available. And if we look up here, you can see it here. It says promise, which means it's available, but it hasn't been actually executed yet. And so we want to know a little bit about trees. And so I could type trees, and I can see it. But if it's really long, this might be difficult to look through. Or I could do head of trees like I did before, and I can look at the first columns. You can see it's got three variables: girth, height, and volume, which are three measures on a bunch of trees. How many trees do I have? I'd like to know that. I can type dim of trees. This will give me the dimensions of this matrix, and you can see we have 31 trees, 3 columns. These are the 3 columns, so there's 31 trees. So that's easy to see. There's some other things that let me peer deep inside. Are if I do str of trees, it'll tell me more like internally how it's stored. So it says this is a data frame, 31 observations, 3 variables. Girth is numeric, height is numeric, volume is numeric, and it actually shows me the numbers. I can do attributes of trees, which is quite similar. This will give me each of the names of trees, or the names, the type of thing it is, and the row names, I guess. In this case, I can also try summary of trees. And this does a statistical summary of each of the variables. So now I can see, okay, here's girth. It's about 13, whatever the units are. Height is about 76, plus or minus, and mean is 30, plus or minus. Okay, so that's what I would often do when I first look at the data, just to get a sense for what it is. It's also useful to graph it. And so I can make a graph. I can plot 2 graphs side by side. I could just try a mat plot of trees and a box plot of trees. So let me zoom in on this to show what it looks like. Here's the mat plot, and we have 3 series. It's going to plot all 31. three values. In this case, they happen to be sort of on the same scale, even though they're different measures. So it makes sense. We can see that actually the first measure, which was girth, it's probably sorted in that order. And then the others generally are correlated with that, but not perfectly. With 3, the volume may be more strongly correlated than 2, the height. And I guess that makes sense. You can have some trees that are tall and skinny, but if a tree has a really large trunk, it's probably going to be broad as well. So this sometimes doesn't make sense, but in this case it's good to visualize. But I can also do a box plot, which gives a sort of box and whisker plot of each of these variables. So I can see, oh, this one is small, this one is pretty large with without too much spread, and this one has a much broader range. So that tells me a little more. Of course, I showed you this earlier. I could look at the head of data, or just some of them. This should be trees. I can look at just the first 5 rows of trees, or I can look at just some of the columns. So this is some of the subsetting we did before. So there's 3 columns. So if I say trees, comma 1 to 2, this will show me just the first 2 columns, and if I plot them, this will plot girth by height. And this is exactly the same thing, or I could do -2, and this will plot girth by volume, and we can see that here again, like we saw earlier, that there's a much stronger relationship. So if you add a negative value, it removes that. That's what this negative is doing here. So since there's 3 of them, adding the negative will just make it the first and the third. So it sort of performs surgery on that data set. And then plot, when you give it a matrix with 2 columns, will plot an XY plot. Okay, so those are some ideas of how to explore a data set when you first see it. That's really straightforward stuff. But you often should get a feel for what is going on. Another really handy thing that I use often, especially for making graphs and doing some analyses, is sorting. So let's start by creating a data set, 500 random uniform variables, and then I'll create another one that's related to this that has noise. I'll put these both in a data frame like this, and we can print this and look at them, and it's hard to know what's going on just by looking at it. So there's a few functions that let us measure the order of things. This is just an example. I've got 2.51, 1.52, and 2.5, and if I look and if I use the order function on that, you can see it says 2, 3, 4, 1, 5, 6. So what's going on here is it's saying 2 is the second element is the smallest. That's 0.5. Then 3, that's 1. Then 4, 1.5. Then 1, that's a 2. Then 5, that's also a 2. These happen to be tied, but so it doesn't really matter what order it is, so it's going to do it in the order that they appeared in this vector. And then 6, 2.5. So that's what order will do. You shouldn't get that confused with rank. If you look at rank, and here we see this, each of rank essentially replaces these with their rank. So the smallest one, which was 2, is the second element, and that's 1, and then 2, and then 3, and then 4 and 5 are tied, so it gives that a rank of 4.5, and then 6. So these are different, and sometimes you want one and sometimes you want the other. It turns out that the order of the order is the rank, except for ties. So if you don't have any ties, the order of the order is the rank. You can see here that except for this 4 and 5 tie issue there, they are the same. So you can use order really easily to sort things. So we have this data, and I get the order of data $y. So I look at here, and it tells me, which one's the smallest, and you can look and find one. That will be the one that's the smallest. And So if I then use this bracketing and put the order of that in, it picks out, it's going to pick them out in in the order that I specified. So here y is the smallest. Number 284 was the smallest. You can see it's negative 0.274. Then each one you see a little increment because of just how the data came out. So this is a way of sorting data. I find the order of something, and then I sort some, and I use this subset to pick out it in that order, and all of a sudden I've sorted it according to that order. It can come in handy in a lot of ways. One is for plotting. Let's look at what happens if I take this data. I've rearranged data 2 so that it's in order. So data 1 and data 2, dat 1 and dat 2 contain exactly the same information, the same numbers, but in a different order. So let's look at what happens. I'll zoom in on this. So the first one is just random, and so if we draw a line between every consecutive point, it's just a spaghetti mess. But here I put them in the right order, so we see that actually every one on the top is connected to the next one down. Now this is not really useful, but it shows that the line shows that I put them in order, and I could maybe do other things by making sure they're in order. And if I only had 10 points that were random and I wanted to put them in order, I could use this to sort them and graph them in order. Okay, so that's sorting. Another thing that you do all the time for data management is called aggregation. Aggregation is creating tables or creating summary statistics where you look at the values of one variable by the values of another. So let's start looking at tables. Here's maybe a mini example voter database. I surveyed 20 people and asked, what's your party, what's your gender, and who did you vote for? And we put these together in a data frame. You can see, you can't quite make anything out of this right at the moment. They're just a bunch of variables. But maybe we want to know how many people were in each party. I can use table of that value, and I say, see, there were 5 D's and 6 R's. Or I could look at gender. Well, there were 5 M's and 6 M's and 5 F's. Or I could look at who they voted for, candidate A or B, and there was a majority who voted for A, minority voted for B, 7-4. So just a table and a set of variables will tell you a listing, an account of all the different levels. It'll even work if you have continuous variables, but oftentimes that's not useful. So you usually want to use this on categorical or text-based variables, character variables. Now I can look at the contingency. I can see not just the gender breakdown, but who they voted for. So if I put 2 variables in, it'll give me a contingency table, gender along the left, and then voting along the right. And you can see if there's a relationship. Here's party by vote, and here the R's were evenly split between the 2, and the D's were 4-1 for A. And the table, if you do all of them, it'll just keep on building tables. So if I give it the whole thing, it gives me, the A. It gives me them like a 2 by 2 by 2. If I put them in a different order, it'll organize them differently. But so this could be handy for making a table for seeing if there's any relationships between a bunch of categorical variables. Of course, we can look at any individual pairs. Gender by vote, party by vote. Oh, we just did that. There's other ways now, if I have this 3 table of slicing it. So I've got X tab, which is this 2 by 2 by 2, but I could go X tab 1 comma comma. Since there's 3 levels, I have 3 possible places, and this will give me, well, it doesn't tell me what it gives me, but you have to pay attention, and these are just the D's, or X tab 2 comma comma will give me just the R's, so that breakdown by that. I can actually refer, because that's kind of difficult. When you have a table like this, you can refer to it by its name rather than its position. So this gives me, the same thing here. This would give me a single row, which happens to be Democratic men. So you can break up this crosstab using subsets here and select rows and columns or in a lot of different ways. Here's another example. Here's 50 values. We'll sample a bunch of magical creatures, unicorns and Pegasus, and we'll sample which types of ice cream they like. We can look at our table A, B, and C. We can look at X by Y to see for A, B, and C, is there a difference among Pegasuses and unicorns? Maybe A, B, and C is which stable they came from. These two things would create the same thing, the contingency table of all 3 of these. I'll save it to a file, and again, I'll save it to a variable, and again, I can specify row, subsets. I can sort of slice it however I want with things like that. Okay, so that's one way to aggregate, which is to create tables, especially of contingencies between categorical variables. There's other types of tables you might want to make, which maybe are means of a continuous variable across levels of a categorical variable. And this you can do with things like aggregate and tapply. So let's create some more data. I've got, again, X and Y are somewhat related. I'll make a data frame. And then I'm just going to make a factor that turns X into bins in a special way. It sort of bins these so that they are in order. So the first thing I might do is try to aggregate. There's actually a couple ways to aggregate. This says I want to aggregate Y based on this factor. So if we look at dat3 or head dat3, I've got this factor which has zeros, ones, twos, negative ones. And I've got a bunch of X's and Y values. And what I want to do is say, collect all of the ones that are 0, all the Y's that are 0, and find the average of those. Then collect all the Y's that are 1, and find the average of those, and 2, and then negative 1, and negative 2, and so on for every value of this. So that's what aggregate does. It takes all the levels here and computes a function on everything that fit for every one of those levels. And I want to compute mean. So if I look at what I was produced here, you can see that there's this pretty strong relationship between X and the bins. And this is the average X value for things that fit in that bin. There's another way of doing this. You could also do aggregate. You could say Y tilde factor. I think data is equal to dat3. Data's not capitalized. Data is equal to dat3. Function is equal to mean. Oh, fun is equal to mean. So this is almost the same, but you can see that here it's called X and here it's called Y. So by default, aggregate the thing that's aggregated will be given the value X, but if you use this syntax, it'll be called whatever you called it here. This can be a little easier to write, but I think everything needs to be in a data frame to do it. in this manner, everything doesn't need to be in a data frame. I can pick out I can aggregate something else, like the x values, and because it's x, it's going to create this whole additional data frame, so I can pick out just the $x and put it on. So now, if I look at this, I've added this column. So I've said I want this new column, and whatever I aggregate for x, but I'm going to pull out just the x value so I don't duplicate the bins, because the bins are going to be the same. Okay, so that's, and now we see that even which was actually the y values, is related, so are the x values, but they're a little different. There's another way to do this, but you can only do one at a time, and that's with the t apply. So the syntax is identical. And you can see these numbers are identical to this, but it labels them by the value. It creates a single table and labels them by the value. So you can have that, or you can have that. And when you have more than one thing, this can be handy because it'll create a matrix. Okay, here's another example that I can use rank here to create some bins. I'll make another factor, and so I want to say I want 20 in each bin or something like that. So I'm going to take the rank, and I'm going to divide by 20, so there should be, rank 1 through 20 will all be less than 1, or all be less than or equal to 1. And then when I apply floor, they'll all be changed to 0. I guess rank 1 through 19 will be all changed to 0. 20 through 39 will be changed to 1. And if I aggregate by this is a slightly different way of binning. And I can do the same things. So I've got these two different ways of aggregating across different levels of something. And we can look at what happens if I plot this. Let me reset here. So this just looks like a line, but what happens is this is the bin value, the mean of the bins, and this is the mean of the actual values. And because I was creating them from the same thing, they're sort of identical. I'm going to then plot the x vals that are created from these two different types of aggregations. And you can see that when I use bins of equal width, it looks like this, like the red, and when I use bins of equal size, it looks the other way. So it's just two ways of sort of making histogramming or bins. It's handy to do in using aggregate. We'll use aggregate and apply, t-apply all the time. Okay, so next we've got another sort of way of aggregating, which is called the apply. This aggregates by rows or columns. So if you've got, say, a matrix, you want to find the average of each row or the average of each column, or you want to apply a function to each row or each column, maybe to find the min or the max, you can use apply. So here let's create a 7x4 matrix. We've got 7 rows, 4 columns, and they're just random numbers right now. But if I take apply m1 and then the name of a function, it will apply this to every either row or column. And if it's a table with 3 dimensions, it'll apply it to the first one. So if you look at this, the first dimension represents a row. It's 1. That's the first element. So this applies it by row. The second one will apply it by column. So here I'm going to see what's the mean of what's the variance of each row actually. I'm going to round it to 3 significant digits. So if you look at each row, I end up with 7 numbers. This row had a variance of 0.05, 0.03, and so on. Here I might want to take the min and the max of each column. So I just have 4. And if you look back up here, 0.056, here's the min. You can go back and track that. And by doing this, it makes it easy to make a plot like this. I can use matplot to plot each of these series, right? This is 7 by 4. There's 4 columns and sort of 7 series. You can think of it that way. And then I can draw lines between all the mins that I just calculated and lines between all the max values. And I could also just plot the means too. So these are the mean values, the min and the max. Some of this, there's a few function, row sums, call sums, row means, and call means, that can do this for means and sums. So I can, I guess this is the same as this line I plotted here. This is, all it does is it's an easy way of calling this apply function. Okay, so that covers apply. So it's altogether we did data, reading in data, saving data, or aggregating data, sorting data, filtering data. And here's something that I'd like to try to use all of them together, or as much of this as possible. We're not going to read the data in because we're going to use a data set that exists. And these are the chick weight. This is the chick weight data set. So you can get this by calling data chick weight. And we can look at, what does it look like? Okay, there's time and body weight. We can say chick weight. It's just weight, time, chick, and diet. So let's think about what's going on here. We've got a bunch of different chicks, little chickens. They're on 4 different diets. They are measured every other day up until they either die or it's the 21st day of their life. And their weight is measured. So maybe we'd like to know if diet has an effect on the weight gain. So this is a really typical data set that you might have in psychology, where instead of chick you have subject. Maybe these are learning curves across people. So I could use table like chick weight dollar chick, and I can see what they are. And this tells me, oh, there's some of these chicks that only had a couple measures. Some had, almost all of them had 12, except for a handful, which had 10, 2, 7, or 8. So maybe a few of these were dying halfway through or were pulled from the study for another reason. So that's another thing that we're going to have to pay attention to. So we can't count on there being exactly 12 measures of each chick for whatever we do. Okay, so let's start by just trying to make some graphics to plot what's going on, and then we'll use aggregation to find means of these things. So here's all the data where I plot time by weight. And you can see that, again, we have measure at day 0, 2, 4, 6, 8, all the way to 20, and then there's a final measure at day 21. So there's a pair of measures 1 day apart, but other than that, it's every other day. So that tells us a little bit about what's going on. We could maybe fit a line through the middle of this and say, well, this is how much chicks grow every day. But there were 4 different diets. So here I'm going to take 4 different colors, and I'm going to make a plot where this is a trick we used before. I'm going to pick the color scheme based on the diet, and we're in luck because diet is coded as 1, 2, 3, 4. So diet 1 will pick out red, diet 2 will pick out dark green, and so on. Okay, so now each of the colors is plotted. They look like they might overlap a little bit, and so it can be hard to know what's going on. But certainly there's a lot of red here and a lot of orange here. So maybe orange is a better diet than red. Well, how would we figure that out? Well, we can figure out, for every time period and every diet, what's the average weight? That's we can do with a t-apply with two arguments in this list. So previously we used t-apply with just one argument. So let's see what happens when we use two arguments. It made this table where I have the different diets as columns and different days as rows and the average of all the chicks on that day. So you can see, luckily at the very first day, they were all very similar average. By the 21st day, they differed considerably. This diet 3 was almost 100 grams heavier than diet 1. So if you're a farmer, this might be something really useful to know. So just to record what the days are, I'm going to record them by hand here, but I could pull them out from the row names here. I could pull them, like the row names of this are going to be text labels, and I can make them numbers, so I can do the same thing like that. And now I'm going to plot this again, but this time I want to make it sort of small circles because I want to downplay the raw data and focus on sort of summary data. So I'm going to do this mat plot where I'm going to take times, which I just pulled out, and the CW ag, which is this matrix, and plot those. So I'm going to lay it on top of here using add. So there's this add argument that allows me to lay them on top of each other. So now we can see that as time progressed, there's different growth rates for the four different diets. In the first few days they don't separate, but even by day 5 there's a difference on average. So if we look at CW by sub, this just redefines the whole data set as a table. So I'm using that t-apply of weight by time and check. This might help, this is basically what's being plotted here. But now I can see, okay, I've got time along this axis and check here, and I've got a bunch of NAs. And the first 3 you can see, well, this one got to 35 and then we don't have any more measures. This one got to 54 and we don't have any more measures. And you can see if you look across the different diets that 54 is actually the lightest. Even here, 35 is the lightest of all of them. So we probably expect that what happened is these chicks either were about to die because they were so underweight or they died. So maybe they were about to die and they got pulled from the study to go on a different diet. Let's see. So I want to figure out an easy way to figure out which chick was on which diet. If I'm using this table, I'd like to know. And so I used aggregate to do that, and it was kind of an abuse of what it does. But so I'm gonna aggregate by chick, and I'm gonna find. I'm going to aggregate diet by chick. So every chick has a bunch of measures in the diet column of the original data, but they're all the same. And so I'm going to find the median diet for any chick. Since they're all the same, it's just going to pull out, the 1. And then I transform it to a character and then back to a number to get diets. So this is just a little trick that you can think of to pull out something that otherwise I might have to code by hand, so I'd like to know there's many observations per chick, and I'd like to know, chick 1 had diet 1, chick 4 had diet 1. Now it turned out when we looked at it that they were all in order, but you know, there's actually more who had diet 1 than diet 2, and there's an unequal number here, and I would have to count them all up to figure that out. So it's this is a way of pulling it out by sort of automatically and not making any coding errors or having to count up and things like that. So I'm going to use that here by going back to that matrix. I'm going to instead of plotting all the points like I did before, I'm going to use matplot to plot it. But so I get one growth rate per chick. I'm going to use those diets to pick the color scheme out. So now the colors are coded by the diet. Then I can plot each individual measure point as well using the original code with the original color scheme. So all the colors of the points are matching the colors of the lines here. And now, since I'd calculated the mean lines as well, this gives me all the raw data, and I can even see like this guy got to day 12 and his data stopped. So I'd like to plot, you know, the means, but these sort of are overlapping. So what I tried is I made a fatter white line here, which sort of erases what's beyond it, because the individual data points don't matter too much. And then I drew the lines on top of it. And then there's other things you can do. I added a title, horizontal segments, which is nice because sometimes it's hard to tell whether things are increasing without that as a guide. 2 different horizontal segments, and a legend, so we can see diet 1, diet 2, diet 4, and then diet 3 is the order of best diets. And this is sort of the final analysis of the final graphic for the chick weight. Now we don't know for sure if these are, say, significantly different, but we've now made a nice graph that illustrates the growth rate over time and illustrates using color and using aggregation the growth rate of the average chick in each diet. And if you're a farmer, you might say, you might look at this and say, oh, you know what? The difference between diet 4 and diet 3 don't appear until day 15, and then they separate. So if you're looking for immediate results, you're not going to find it. But they're both going to separate from the other ones. Maybe you recognize that diet 3 is 50 cents a pound more expensive than diet 4, and you could use this to make a decision about, is it worthwhile getting this more expensive diet to gain another 25 milligrams weight by the day 21. All right, so that is it for walkthrough chapter 2, which just covered issues of aggregation and data management. And let's see, there are a number of exercises here that we skipped over, and those answers are in the back of the chapter. All right, well, thank you.